Hello everyone, welcome to my channel. My name is Ravi Singh and I'm going to help you understand great engineering concepts around us. For that, you just need to hit the subscribe button down below. This video is made for the purpose of answering the question which I gave you in the previous video. And the question was, even though sound travels faster in warm air, it travels farther in cold air. But why? So let us first discuss about what the sound is. So sound is nothing but a local disturbance generated by a sound source. And what the sound source is, like a stereo speaker or say tuning fork. So these are the source of the sound, and from here the disturbance propagates in the medium. Now this disturbance is actually in the form of vibrations of the particles in the medium. So suppose I am having a stereo speaker here, and if I am starting this stereo speaker, then it creates vibrations in the surrounding medium at first, and if this stereo speaker is continue its vibrations, then these vibrations will travel farther in the medium surrounding it, and this actually creates a wave. That is what? A sound wave. Now most of us have a wrong perception that the medium also travels with the sound. That medium also travels with the sound. When the vibrations are there created by the stereo speaker or any other sound source, then the particles in the medium is also travels with the sound wave. But that is not actually the case. What happens is, when the source creates the sound and the wave is created and it is traveling, then these molecules vibrates and pushes the adjacent molecule. It just pushes the adjacent molecule, and then it just pushes the other molecule, and this just pushes the other molecule. So overall, the average position of a particular molecule is not going to change. The average position of the particular molecule is there only. Only it creates vibrations, and thus the disturbance is transported by these molecules in terms of vibrations. Now during propagation, like when the sound wave is traveling, during propagation, just like any other waves, sound waves also reflected, refracted and attenuated by the medium through which it is traveling. Now what is this attenuated? Attenuated means, like any other wave, when sound wave is traveling through the medium, then the intensity flux of the sound is going to decrease, like the energy intensity is going to decrease because of some losses as the sound wave is traveling through the medium. So that is the meaning of attenuation. Now sound is transmitted through, say, gases or plasma or liquids as longitudinal waves. While when it is traveling through solids, then it will be either as longitudinal wave or transverse waves. So it is nothing like sound is only a longitudinal wave, but when it travels through gases, plasma or liquids, then it travels as longitudinal waves, while through solids it can travel either as longitudinal wave or transverse waves. But what are these longitudinal waves and what are these transverse waves? Basically, longitudinal waves are waves of alternating pressure disturbances. or say alternating pressure deviations. Deviations from where? Deviations from equilibrium pressure. In the form of regions of compression and rarefaction. So that is what a longitudinal wave is. Like, it is a wave of alternating pressure deviations from equilibrium pressure in the form of regions of compression and rarefaction. That's how it travels. While transverse wave is alternating regions of alternating shear stresses in the right angle to the direction of propagation of sound. Propagation of sound. Like, if sound is traveling in this direction, then perpendicular to it, like in this direction, there is a alternate shear stresses, and that's how it travels in case of transverse wave. And in longitudinal waves, I already said, alternating pressure deviations from equilibrium pressure in the form of regions of compression and rarefaction. Now, upon solving the wave equation for the propagation of sound, like there is a wave equation and for the propagation of sound, and upon solving that wave equation we will get the sonic speed, that is the speed of sound, and that comes out to be under root dp by d rho. Now this is sonic speed. As I said in one of my previous video, that sonic speed is the speed at which disturbance in terms of pressure perturbation travels through the medium relative to the medium, relative to it. So that is the sonic speed, speed at which disturbance in terms of pressure perturbation travels through the medium relative to it, relative to the medium. And sound wave is also a type of weak pressure wave and having the same nature of pressure perturbation as it travels through the medium. So this sonic speed can be said as the speed of sound, but in every case this not prevails, as I said in the previous video also. So just think about it, just mind it. Now this equation, on solving this wave equation for propagation of sound, dp by d rho, this is actually related to the elastic property of the medium. This is related to the elastic property of the medium. Why? Because as we know that bulk modulus K is, this is bulk modulus of elasticity, and this can be written as the ratio of change in pressure, I am writing it in differential form, upon change in density by original density. Okay, so from here dp by d rho can be written as under root, from here dp by d rho can be written as k by rho, and upon substituting it in this equation, c can be written as under root k by rho. So it is quite clear from here that this contains the term bulk modulus of elasticity. So this is somehow related to the elastic property of the medium. And since this is elastic property of medium, so the medium is elastic, medium is not rigid, which means if I am having any disturbance in the medium, created by a source of sound, say stereo speaker, then that disturbance needs some time in order to get from here to say some distance x. It means that if I am creating a disturbance here, then it takes some time to reach a distance x, and this is certainly not infinity, like c is not infinity because the medium is not rigid, medium is elastic, so it needs some time. And this speed of sound under root k by rho, this is the bulk modulus of elasticity, and this is the density. So if I am talking about a medium, a particular medium, then the speed of sound in that medium depends upon the bulk modulus of elasticity of that medium and density of that medium, the ratio of these two. So let us talk about solid, liquids and gases. Solid, liquid and gas. This bulk modulus of elasticity, it basically depends upon the interatomic bonding of the particles within the medium. So if the medium is more strongly bonded, as in case of solids, then the bulk modulus will be more. Strong bonding, more bulk modulus. So the bulk modulus in case of solids is more, and in case of liquids it's intermediate, and in case of gas it's least. So this is the order of bulk modulus. Like for solids it is more, then for liquids, then for gases. So this is the order of bulk modulus. And about the density, obviously the density of solids is more than the density of liquids, and that is more than the density of gases. So this is the order of density, and this is the order of bulk modulus k, and the speed of sound is the ratio of under root of the ratio of k divided by rho. So if I am telling that for solids k is more, then for solids density is also more. So this is also highest for solid, and this is also highest for solid. So the speed of sound will be greater in which medium, solid, liquid or gas. So that depends upon the value of this ratio. So the bulk modulus in case of solids is higher to nullify the effect of high value of density. Like obviously the value of density is high in solids, but the value of bulk modulus is so high that it nullifies the effect of density, and that's why the overall ratio k upon rho is more in solids. Similarly in case of liquids it is second, like this is first, this is having the highest speed of sound, and second when again we will go ahead and take the ratio of this k by rho, then in comparison to solids it will be less, the speed of k upon rho, and it will be more than the value in case of gases. So the overall speed of sound is highest in case of solids, then in case of liquids, and then in case of gases. So the speed of sound in gases is least, and the speed of sound in solids is highest. Now coming to gases, specifically air. When sound propagates through air, then that process is considered to be isentropic. That is reversible adiabatic. That is, the propagation of sound through air is considered to be an isentropic process, that is reversible adiabatic process. And this air obviously we can take it as an ideal gas. So in that case, the speed of sound can be written as del P by del rho at constant entropy. This S denotes entropy, and this can be further simplified to under root of gamma P by rho. Gamma is the ratio of Cp by Cv, and that is further simplified to under root gamma RT. So in case of air, the speed of sound is approximated as under root of gamma RT. So now from here, this is the ratio of specific heat Cp by Cv. This is universal gas constant, and this is T, that is temperature. This is R bar upon m molecular weight, and this is Cp by Cv. So this is universal gas constant. So now it is clear from here that when the temperature is more, then the speed of sound will be more. So this is all about air. So if air is warm, it means that the temperature of air is more, then obviously the C will be more, and then the sound will be more. Speed of sound in warm air is more. So that's why this sound travels faster in warm air. Now, as a matter of fact, it is not only the temperature of sound, the temperature of air that affects the speed of sound, but there is one more thing that is quite important, and that is humidity, the amount of humidity within the air. That is nothing but H2O. So when air is having more humidity, then obviously the amount of oxygen and nitrogen per unit volume will be less, because that space is occupied by this H2O, humidity. And when this oxygen and nitrogen is less and this humidity is more, then as we all know that H2O is having the mass of 18 grams, oxygen is 32 grams per mole, I am telling, and nitrogen is 28 grams. So this is lowest among these three. So if this is more and these are less, then the mass is less overall. The whole mix mass is less because this is more while these are less. So the density will be less because of that. And if the density is less, then according to this relation, if this is less, then this speed of sound will be more. So this is another factor, that when air is having more humidity, then the speed of sound will be more, and when the air temperature is more, then the speed of sound is also more. So humidity is also an important parameter to judge the speed of sound in case of air. That was all about why sound travels faster in warm air. Now let us see why sound travels farther in cold air. For that, as we all know that sound is a wave. Sound is what? A wave. So when it travels from hot air to cold air, or from cold air to hot air, then just like any other wave, as example light, this also refracts. Sound also refracts. Because the speed of sound in hot air and cold air are different. It is lesser in cold air and it is more in hot air. So when sound travels from hot air to cold air or from cold air to hot air, it refracts like any other wave, for example light. Now let us take the example of a hot day. So with this picture. Now suppose the day is hot and I am having a bell on the top of this tower. Let us suppose this is a bell, and there is a person standing here, and this is, I am talking about a hot day, so the ground is hot in this case and the air is cold, because this is, I am talking about hot day. So because of this, the speed of sound is more here and less here. The sound coming from here will move away like this. So This is the process of refraction in this case. Like the sound travels, first comes closer to ground and then it will go away. It will like form a upward bending like this. And that's why this person can't able to hear the sound from this tower which is far away. So this is a case of hot day. Now let us see what happens in case of cold day. In case of cold day, the ground is cold. And this is again tower and a person standing far away from this tower. So in case of cold day, the ground is cold and the air is hot. So in this case, the sound will bend downward, or it will have a shape like this. It will travel from here, go upwards, and then it will come downwards like this, and hence the person is able to hear this sound from farther away because of the refraction in this manner. But and this is why sound travels farther in cold air on a cold day and not so far in case of hot day. But there are a lot more which makes winter seasons quiet, and that helps sound travels farther. And that is, like in case of winter season, people basically avoids gathering outside the house. They basically want to remain inside the house in the winter season, and that's why there are lesser vehicles on the road, less number of people roaming outside, as I told you, and animals also stay quieter in case of winter season, and that's why sound travels farther in case of winter season. So this is also the reason. So this is all about this video. Thank you.
Also, for more exciting contents about science related stuffs in the form of news, videos or articles, don't forget to like our page Science Talk on Facebook, for which the link is given below.